So today we will discuss about a problem. The problem is draw the polar plot of an open loop transfer function. The transfer function is given as g of s is equal to g of s equal to 6 divided by the transfer function is given as g of s is equal to 6 divided by s plus 1 into s plus 2. So sketch the polar plot of the given open loop system having the transfer function 6 divided by s plus 1 into s plus 2. Also determine the phase margin and gain margin of the given open loop system. So here you can see that g of s is given and h of s, we can take h of s as unity, hence the open loop transfer function as our open loop transfer function will be 6 divided by s plus 1 into s plus 2. Now we can convert it into 1 plus st format. Now when you convert it into 1 plus st format, it will be 1 plus s into 1 plus 0.5 s, here it will be into 2 . Now we can rewrite the equation g of s is equal to 3 divided by 1 plus s into 1 plus 0.5 s, and the sinusoidal transfer function, we can rewrite sinusoidal transfer function g of j omega as 3 divided by 1 plus j omega into 1 plus 0.5 j omega. Now for drawing polar plot, we have to find out, first we have to find out corner frequencies. Here we can see that omega c1 is equal to 1 radian per second and omega c2 is equal to 1 divided by 0.5, that is equal to 2 radian per second. Now the next step is for different values of omega, that is in and around the corner frequencies, we have to find out the real part and imaginary part of the sinusoidal transfer function g of j omega. That means we have to find gr of j omega, that is the real part of sinusoidal transfer function. Also we have to find gi, that is imaginary part of j omega, for different values of omega in and around the corner frequencies. So in order to find out different values of real part and imaginary part for different corner frequencies, what we have to do is we can start from a frequency which is lower than the lowest corner frequencies, and we can gradually start increasing the frequency and we can find out the values of sinusoidal transfer function. So we can do it in calculator. If you want, you can write the magnitude and phase angle of g of j omega in polar form. So in polar form, the magnitude of g of j omega will be 3 divided by square root of 1 plus omega square into square root of 1 plus 0.5 omega square. So and phase angle of g of j omega will be tan inverse minus tan inverse omega minus tan inverse 0.5 omega. So in Bode plot we are actually finding magnitude and phase angle in polar form, and then we are plotting the border plot. But in polar plot, if we are drawing the polar plot in ordinary graph sheet, we have to find out only real and imaginary part of the sinusoidal transfer function. So these are the values, these are different values for omega. We have find out the real value and imaginary value of the sinusoidal transfer function with respect to different values of omega. So here you can see that I have taken the value of omega starting from 0.1, because our lowest value of corner frequency is 1, and I have taken the value up to 5. After 2, I have taken 2 more values, 2.2 and 5. So this is actually in order to just draw the border plot and to get the final value, in order to draw the polar plot and in order to get the final value of polar plot. So the next step is we have to mark the real axis and imaginary axis in the ordinary graph sheet, and after that we have to plot the polar plot with respect to these coordinate values, that is with respect to the real value and imaginary value of the sinusoidal transfer function. We have to plot or sketch the polar plot in the ordinary graph sheet. So what is the next step? The next step is we have to mark the scale, x axis and y axis. Also we have to mark the scale. So please remember that when you take the scale, take x and y axis as uniform scale. So you can see that our maximum value of real part is 3 plus 3. So the scale in the positive side of real axis is I am taking up to 3, and maximum value of imaginary part is up to minus 1.6. So here you can see that in the negative side or minus j omega side, it is marked up to minus 2. Now what is the first coordinate? First coordinate is 3 minus 0.4. So corresponding to 3 and minus 4 approximately, I have marked the small point, and the next coordinate is 2.8 minus 0.85. So 2.8 approximately here and minus 0.84, that is the next point. And the next coordinate is 2 minus 1.7. 2 corresponding to 2, we have to mark 1.7. Now the next coordinate is 1 minus 1.89, corresponding to 1, that is 1.89. Now the next value is 0.6 and minus 1.8, 0.6 corresponding to 0.6 and 1.8. Next value is 0.25 and 1.6. 0.25 and 1.6, that will be approximately here. And the next value is minus 0.07, that we can take approximately as 0. At minus 0.07, the value is minus 1.3. So it will be here, approximately here. Now minus 0.2 corresponding to the omega 1.7, the value is minus 0.2. And minus 1.4. So minus 1.2 will be approximately here and 1.14. So the point is here, the point is corresponding, it is actually changed into the next quadrant. And minus 0.3 corresponding to minus 0.3, the value is 0.9. So this is corresponding to 0.9. Now minus 0.33, 0.76 here only. and the last value corresponding to omega 0.5, you can see that the value actually decreases again, that is 0.18 and minus 0.12, that will be approximately here. So, you can see that at higher frequencies it will move to towards the origin. When you take very high frequencies, you can see that the polar plot will move to origin. So, you can see that it is starting approximately here. Okay, it starts from here, the polar plot starts from here. This is our plot. Now it moves and we have to join all the points. So, you can see that we have to join all the points and draw a curve, a smooth curve, and our polar plot, approximate shape of polar plot is like this when omega starts from 0 to infinity. At higher values or when omega is infinity, it will end to the origin. So, here in this problem you can see that the polar plot actually does not crosses the critical point minus 1 plus j 0. The critical point is the point at the critical point is the point at the negative side of real axis minus 1 plus j 0 point. Here in this problem, corresponding to this problem, the polar plot does not crosses the negative part of real axis. It actually goes to 0 before crossing the negative side of real axis. And what is our equation for, in order to find, what is our equation to find gain margin? The gain margin is, we can find the gain margin using when the polar plot crosses the negative side of real axis, the value of the magnitude of polar plot at when it crosses the negative side of real axis, that value we have to take. But here you can see that actually the polar plot does not crosses the negative side of real axis, and the value of GB is 0 here, since it does not crosses the negative side of real axis. Since the polar plot not crosses the negative side or minus sigma side of real axis, we can say that GB, the magnitude corresponding to the crossing point, is actually 0. And what is our gain margin? Our gain margin is 1 divided by GB and modulus GB, and that is equal to 1 by 0, that is infinity. Okay, 1 divided by modulus GB, and that is actually infinity. Now, here in this problem, we will not be able to find omega PC also, because we do not know the point at which the frequency at which the polar plot converging to origin or 0, and corresponding to that we will not be able to calculate omega PC. We will not able to calculate omega PC, but we can find what? We can find the gain phase margin and gain crossover frequency. So, how can you find the phase margin? In order to find the phase margin, we have to plot a unit circle corresponding to from as origin as center and 1 as radius. We have to plot a unit circle. So, it will be approximately like this. We have to plot a unit circle as origin as center and 1 as radius, and when this unit circle meets the polar plot, mark that point. when this unit circle meets the polar plot, we can mark that point. So I am marking that point as B, this point where the polar plot meets the unit circle, mark that point as B, and from the origin draw a straight line to the point B. Okay, from the origin draw a straight line to the point B, and we have to measure this angle. Then we have to measure this angle. This angle we have to measure, and I can mark it as phi GC. So we will get phi GC is phi GC, when you measure that angle, you will get phi GC is approximately equal to 105 degrees. And what is our phase margin? Phase margin gamma is equal to 180 plus phi GC, and we can see that when you take or mark the angles in clockwise direction, we have to put a negative sign here. So phi GC will be negative or minus 105 degree. When you measure the angle in clockwise direction, always put a minus sign, or negative angles will be in the clockwise direction and positive angles will be in the counterclockwise direction in a polar plot. So we have measured the angle in clockwise direction, so phi GC will be 105 degrees, and gamma is equal to, or phase margin, gamma is actually what? Gamma is phase margin, that is equal to 180 degree plus minus 105 degrees, that is equal to approximately 75 degrees. 75 degrees, that will be your phase margin. So what will be omega GC? Omega GC will be the frequency at the point corresponding to B. Okay, because the polar plot meets the unit circle here at this point B, and the frequency corresponding to this point B will be omega GC. Now what is omega GC? Omega GC is the frequency at which the magnitude of open loop transfer function is unity or 0 dB. So here when we plot the unit circle, the magnitude at this point B will be unity. So corresponding to this point, the magnitude of the polar plot or magnitude of the open loop transfer function is unity, and hence the frequency corresponding to this point will be omega GC. Now how can you calculate omega GC? In order to calculate the omega GC, there are two ways. Either you can separate from this point corresponding to this point B, you can find the real value and imaginary value of the point B. Corresponding to point B, we can find the real value and imaginary value or coordinate corresponding to point B. So from that you can calculate omega GC, or we can calculate omega GC. Actually we know that what is omega GC? Omega GC is the magnitude of open loop transfer function is unity. So what is the magnitude of open loop transfer function? Open loop transfer function's magnitude is magnitude g of j omega. We can write the equation of magnitude of open loop transfer function, that as g of j omega equal to 3 divided by 1 plus omega square into 1 plus 0.5 omega square. So, when at omega GC, the magnitude of G of j omega will be unity. So, we can calculate this by substituting in this equation. That means the magnitude as unity 1, and find out the value of omega GC corresponding to this value, corresponding to this equation. When you find out the value of omega, that will be the value of omega GC. This is one method. Another method is that, okay, another method is that corresponding to the point B, that means where the unit circle meets the polar plot, corresponding to that point B, we have to find out at point B, at point B, you have to find out the real value of j omega and imaginary value of the open loop transfer function from the graph. So, when you know the real part and imaginary part, we can separate the equation. We can separate the equation 3 divided by 1 plus j omega into 1 plus 0.5 j omega as real part and imaginary part. By separating the equation and by equating the real value obtained from the graph, also we will be able to find out the value of omega. That will be omega GC, because we are finding out the value at the point B. That point will be the omega GC value. Now, the question is only you have to find out the gain margin and phase margin. So, gain margin is infinity and phase margin is 75 degree approximately, and here you can see that there are no negative signs, both are positive. Gain margin is infinity, then also it is positive. Then you can say that the system is stable system. Okay, the system is stable system. Now, I am just saying how can we draw approximate polar plot. We can find out that the approximate polar plot will be like this. How can we draw that? That is I am going to tell you now. So, for that, just drawing the real axis and imaginary axis, you can see that real axis and imaginary axis. Now, mark the angles corresponding to each axis. That is, here it will be 0 degree, here it will be minus 90 degree and minus 180 degree. Actually, this is corresponding to minus sigma, and this will be j omega. Here the angle will be minus 270 degree. This is corresponding to minus j omega. Now, what is our equation? Our equation of the system for the given system, our equation is of open loop transfer function is 3 divided by 1 plus j omega, 1 plus j omega into 1 plus 0.5 j omega, or we can write in S terms, that is g of s. What is g of s? G of s is 3 divided by 1 plus s into 1 plus 0.5 s. This is our g of s. So, what is the type of this system? Actually, type of the system is the type of s raised to n term. Then the type of the system is the number of n in the s raised to n term in the denominator, or number of open loop number of open loop poles at the origin. The number of open loop poles at the origin. So the type number is actually the type number related to the number of open loop poles at the origin. In order to have open loop poles at the origin, you should have an s raised to term in the denominator. So here you can see that there are no s raised to term, no integral terms in the denominator, only there are two first order terms. Corresponding to integral terms, you can see that there are no integral terms in the denominator, and otherwise we can say it as s raised to 0. S raised to 0 means it is equal to 1. So what is the value of n here? The value of n here is 0, and the system is type 0 system. Here we can see that the system is type 0 system. The type 0 systems polar plot starts from here. That when a system is type 0, its approximate polar plot, when you draw the approximate polar plot, type 0 systems polar plot starts here. Now what is the maximum phase angle corresponding to the given system, open loop system? Here you can see that there are two first order terms, and the maximum phase angle at the higher frequencies will be what? As I have already told you, when you in the Bode plot, I have told you the maximum phase angle will be corresponding to number of open loop zeros and number of open loop poles. Here you can see that there are no open loop zeros, only open loop poles are present in the given system. So what will be the maximum phase angle? Maximum phase angle will be the number of open loop poles, that is 2, because there are two first order terms, 2 into minus 90 degree. So the maximum phase angle at higher frequencies will be minus 180 degree. Okay. So the maximum phase angle at higher frequencies will be 180 degree. So the maximum phase angle is minus 180 degree. And what is the coordinate? So corresponding to minus 180, what is the maximum phase angle corresponding to minus 180? The quadrant is this quadrant. So the quadrant is this quadrant, because here you can see that this is the quadrant which has the angle in between minus 90 to minus 180. So since the maximum phase angle is minus 180, so minimum will be it can vary up to starts from 0. The phase angle will starts from 0 and it will increase and it will move to minus 180 at when omega is infinity. So the quadrant will be in between minus 90 to minus 180, and this quadrant will be the quadrant corresponding to maximum phase angle, that is minus 180. So the polar plot that starts from here corresponding to type 0 system, and it will end corresponding to the phase angle of order of the system. So this will be the approximate plot of approximate polar plot corresponding to the given problem. So here also you can see that our polar plot is actually similar to what is drawn now. So by this method you can actually get an approximate plot and check that whether you have got the correct answer. Thank you.